Hi, we are back again in the session 5, yes. And earlier we have talked about some important things and we came with some numericals. And we did some numericals for which is useful for board exam and as well as for your competitive exams. Hope you might have practiced the problems in different models. And here is one more interesting problem here, a numerical. Competitive numerical here. You can understand it easily because earlier you might have understood very well the concepts. Look at the numerical ones. Three charges of equal magnitude Q are placed at the vertices of an equilateral triangle of side L. How can the system of charges be placed in equilibrium? Now here, and this is the equilateral triangle. Let me keep it here. And each side is L. Okay. And now here, three charges of equal magnitude. Let this be A, B and C. So here the charge Q is kept and here also Q and it is Q. Equal magnitude means all are in the same sign, so let it be plus Q. It is already given as Q, so Q plus Q plus Q plus Q here. Now how can the system of this complete system be in equilibrium? For this complete system to be in equilibrium, what we have to do? Let us see first let us understand the process and then we'll go with the problem. Now here, the three should be in equilibrium means the force exerting on here it should be 0, here it should be 0 and here also it should be 0. So to make it 0, so let us think once clearly here. So to make the force exerted on this to be 0, there should be some other charge which should be kept, which makes the force exerted, the net force on this particular point at this particular point is 0. Similarly here, because of the charge it should be 0 and because of the same charge it should be 0. So where can we keep that charge? Usually we can easily understand because it's a equilateral triangle, it will be at the centroid of the triangle. So at the centroid of the triangle we are going to keep a charge, let it be some Q. So because of this charge, the net force on this will be 0 and this should be 0 and this should be 0. So now let the charge Q be placed at centroid. Okay. So after this, now let us just concentrate or focus here. And let's find out what is the force exerted on A by B and C. The force exerted by C on A, it will be in this direction because both are positive, it will be pushed apart. So this is F on A by C, let it be some F1. And the force on A by B, it will be both are positive and it is pushed apart and it is F on A by B. Let this be F2. So these two are the two forces and let's find out the value of this F1 and F2. So F1 is, just applying the Coulomb's law here, it is 1 by 4 pi epsilon naught, or you can take it as epsilon, no problem. Because if you assume they are in the error vacuum, you can take it as epsilon naught. If you just assume it as taken in any other medium, you can take it as epsilon. It will not make any change there. So now here, what are the two charges Q and Q? It is Q square. And the distance between them, radius, or the radius vector is L. Q square by L square. And F2 is 1 by 4 pi epsilon naught. So they said same thing here. It is Q and here also it is Q. So it is Q square by L square. You just observe this F1 and F2, they are same. F1 is equal to F2. Now, because of this in F1, F2, the resultant will be there. If we just see here, the resultant will be in between, because these two are equal in magnitude, and we know this angle between this F1 and F2, it will be equal to this angle here, because these two are opposite. And here it is in the equilateral triangle, this angle will be 60, so this also will be equal to 60. So here F1 and F2, the angle between them, theta, is 60 degree. So these are the two vectors, F1 and F2 with some angle theta. The resultant is given by, you know the formula how to find the F net. F net is square root of F1 square plus F2 square plus 2F1 F2 cos theta. Now, you know that now we just go the problem like this, we cannot complete the problem quickly. So instead of taking it as F2, we can take it as F1. So by that we can solve the problem easily. So now F1 square, instead of F2, F1 square, 2F1 F2, it is F1 and it is cos theta. Cos theta means it is cos 60. So what is the value of cos 60? It is 1 by 2. So it is square root of F1 square plus F2 square, F1 square plus 2F1 square. Cos 60 is 1 by 2. Get cancelled. So now it is root of 3 F1 squares are there. So root of 3 F1 square. So that is root 3 F1. So your resultant is root 3 F1. And you know what is F1? 1 by 4 by epsilon naught Q2 square by L, Q square by L square. So if you just look at this F net here, F1 plus F2. This force and the force exerted between A and Q, or this the Q and small q and capital Q here, to just get the force balancing here, these two should be equal and opposite. So now what is this force on A by, let us make this as some P, or let us be C, centroid C. F on A by C is, it is 1 by, now I am going to find the force between the small q and capital Q here, 1 by 4 pi epsilon naught and small q, capital Q. And what is the length between this A and C? This you should know here. You know already this is the altitude of this equilateral triangle, and it is given by root 3 by 2 A. Here it is root 3 by 2 L. Sorry, this side you should know this. What is this? Root 3 by 2 L. Okay. But this complete altitude is root 3 by 2 L. So h is equal to root 3 by 2 L. Now I don't want this complete one. I want length from A to C. How to find this A to C? You know that this is divided in the ratio of 2:1, and this is from A to C, it is 2/3 of this, 2/3 of h, and this is 1/3 of h. So now it is the length AC is equal to 2/3 of h. So that is 2/3 of root 3 by 2 into h is, root 3 by 2 L. So you got it as L by root 3. So this length is L by root 3. So Q, small q, capital Q, and this R square. R square is L by root 3 whole square. So now this FAC and the net F net, how they should be, to just make this, to make the forces balanced here, or the net result should be 0. How it should be means equal and opposite. So FAC is equal to minus of F net. What is FAC here? We got it as 1 by 4 pi epsilon naught. I'll make it here. F AC should be minus F net. What is FAC here? 1 by 4 pi epsilon naught minus F net is, here it is root 3 F1. It is root 3, sorry, 1 by 4 pi epsilon naught Q by L square by 3 whole square. I have made it as a whole square. It is minus F net means root 3 F1. It is root 3. F1 is 1 by 4 pi epsilon naught Q square by L square. So here 4 pi epsilon naught goes away on Q, and this square goes away. L square goes away, and this 3 comes to the numerator. So 3Q by, nothing is remaining. So 3Q is equal to minus root 3Q. So that is root 3 and it is root 3. So Q is equal to minus Q by root 3. So what charge you have to keep at the center means Q is equal to minus Q by root 3. Okay. So now in this problem what we did, very simple here. To make the charges in equilibrium, because it is a triangle, we are going to keep a charge Q at the center. Suppose if it is a line, if there are two charges Q and Q, so to just make the system equilibrium, we have to keep a charge somewhere in between. So applying the same principle here. So now finding F1 and F2, and because here we just found, here if it is Q minus Q by root 3, here the net result is 0. If it is minus Q by root 3, here also the net result will be 0, and here also net result will be 0. So thereby the entire system is in equilibrium. Okay. Now take a screenshot and then we'll move. Okay, now we'll go with the concept, an important concept here. So now, suppose if a charge is there at a point, here is a point is there, suppose if I am keeping some charge Q, and if this is experiencing some force, if it experiences some force, that means it is placed in field called as the electric field. So now we understood that if you are going to keep a charge in a region and if it is experiencing some force, then that region or the space you will be calling it as the electric field. So like that you can define the electric field, or this is the region, electric field is the region or space in which its influence is felt. Whose influence is felt? The field influence is felt. So now you can write the definition like this. Electric field is the region or space in which its influence is felt. Simple, right? Now, one more thing we can understand about this electric field. How this electric field is created? It is created by some charge. Then only we can exert some force, right? So now, electric field is created by charge, and one more thing we can tell about this electric field, it exerts force on. So electric field is created by some charge, and electric field exerts force on a charge. So that's like this, you can keep it in your mind. And now, after understanding this electric field concept here, now let us go with the next one here. Now in this region means electric field. Now if you are going to keep at point P some unit positive charge, if you keep a unit positive charge, now certainly you can say it exerts some force. The force is exerted on it. So how much force is exerted means let it be some F force is exerted on this charge. Now I can say here the force exerted on this at this particular point is F, and it is due to this electric field. And here electric field intensity, the new term here coming here, it is electric field intensity. What is this electric field intensity? It is nothing but it is the force experienced by unit positive charge placed at a point. So the force experienced by the unit positive charge at this point is electric field intensity, or intensity of electric field. So E is equal to F. When E will be equal to F when it is unit positive charge, that is it carries 1 unit of charge. Instead of this 1 unit of charge, suppose if you are going with some test charge Q0, then your E will become E is equal to F by Q0. Instead of this Q0, if you are going with some charge Q, then your electric field intensity will be equal to F by Q. So now we got expression here. Suppose if charge Q is placed in an electric field, then at a point P. At that point P, the electric field intensity is given by F by Q. So this is an expression here. Finding out this expression, you can write its SI units. So the SI units of electric field intensity E is Newton per Coulomb. F is in Newton, Q is in Newton per Coulomb, and one more unit is there, that is volt per meter. Okay. So now this electric field intensity is a vector quantity. This electric field intensity is a vector quantity, and we represent it as E bar. If it is a vector quantity, we have to tell about its magnitude and as well as direction. The magnitude you can find out by this equation, E is equal to F by Q, and direction of E at a point, at this particular point, is the direction of the force acting on the charge at that point. That means it is in the direction of force at that point. Why I am saying again and again at that point means here, between, if the point is somewhere here, that means if its location is changed, there the force experienced may not be same. It may be some Fx or some like F2, some other force will be there, and if the direction of this is in this direction, it may be in some other direction. So at a particular point, the direction will be set in this manner. So E will be in the direction of force at that point. So it's a vector quantity, and the direction of this electric field intensity will be in the direction of the force acting at that point. Okay, now coming to let us talk about two more things here, that is uniform electric field and non-uniform electric field. When the field is said to be uniform and when the field is said to be non-uniform. Suppose in a region, at each and every point, if the magnitude and direction is same, then the field is said to be uniform. Just you can imagine how to represent it, or you can understand how we can represent it in the form of a diagram. This uniform, now we talked about the uniform, and we have to show that the magnitude should be same at each and every point and the direction should be same. How it is possible? Just by representing like this, equally spaced parallel lines. So now by just looking at this, we can say here the field is uniform. At each and every point, the magnitude and direction is same. And if you go for this non-uniform electric field, when the field will be non-uniform, if the magnitude and direction is not same at each and every point. So now, just we can show it like this. The direction is not same. If the direction is not same, certainly E is not same. If the magnitude is not same, E is not same. So we can represent it like this. Okay, just take a screenshot of this and just make a note of that. Okay, now after understanding this concept of electric field, intensity of electric field or electric field intensity, now we will find out the electric field intensity at a point placed at some distance from a charge. Suppose if a charge Q is there, and now I'm going to select a point P somewhere here, and let this point be named as A. Now it is at a distance R. Now, how to find the electric field intensity at this point? Electric field intensity at that point. Already we understood by the definition of electric field intensity. Electric field intensity is the force experienced by unit positive charge placed at a point. So for that, what I have to do here, I have to place a unit positive charge. So if you place a unit positive charge, now what is the force? What is the force of interaction between these two? It is, now electric field intensity is the force. What is the force here? It is 1 by 4 pi epsilon naught and Q and 1. Q1, the distance between them is R square. So it is E is equal to 1 by 4 pi epsilon naught Q by R square. So now from this expression you can understand that the force experienced by a point, now no need to imagine or just keep in mind that unit positive charge is kept at that point. Simply you can find out what is the electric intensity at some distance. Suppose if it is some, let it be some T. What is the at P means? Simply you can write as 1 by 4 pi epsilon naught electric field intensity at some P2 is 1 by 4 pi epsilon naught. It is due to Q and the distance is T square. That's all. Okay. So like this you can find out the electric field intensity at P. So now and then suppose if about the direction, I'll talk about the direction. Suppose if it is plus Q and a charge is positive and your P is here and it is point A. By the magnitude point here, the direction will be in this direction. It is AP from A to P. That means it is in that direction. It means pushed away from this positive charge. If it is minus Q, it is A and it is at point P. Now it will be in this towards the charge. It is pushed towards the negative charge here. So electric field here in the positive case it will be in that direction. The electric field intensity in this negative charge, the negative charge due to negative charge will be towards it. Okay. So like this, keeping in your mind, you can find out the magnitude and as well as the direction. Okay. Now after understanding this concept, to understand the electric field, you have to understand. Actually, to understand the electric field, we have to understand electric lines of force. We can define electric field in another term also. It is the region or space up to which the lines of electric force are extended. The lines of electric force are extended. That means up to what extent the lines of force are extending, that particular region we will be calling as the electric field. So now we define electric field in terms of lines of force. So it is the region or space up to which these lines of force of electric field, the electric lines of force are extended. So now, what are these electric lines of force? So this was introduced. This concept of lines of force was introduced by the Michael Faraday. Concept of electric lines of force as well as magnetic lines of force was introduced by Michael Faraday to understand clearly about the field, electric field, and the terms related to this electric field. And now here, what are electric lines of force? Actually, the electric lines of force will not exist. They are just imaginary. So these are electric imaginary lines of force. Here the lines of force are imaginary, but the field is not imaginary. Okay, so keep that in mind. So now here these electric lines of force. These are imaginary lines. Imaginary lines. How we can draw these imaginary lines? Before just drawing these lines, you have to keep one thing in your mind. If these are what you call it as imaginary, these are the curves or the lines. So if these are the curves or a line, if you are going to draw a curve, certainly here at a point, let us select this point as A. Now at this point, if you draw a tangent to this curve, that tangent should indicate or show the direction of field at that particular point. So if you are drawing a curve, for the curve at a point, if you draw a tangent for the curve at a point, if you draw a tangent, so at this point, if you draw a tangent, there it should indicate or show the direction of the electric field intensity. So now these are the imaginary lines drawn. The tangent at a point gives the direction of the electric field. So like this, we can understand these electric lines of force. Okay. Now, just take a shot and then we'll go with. Okay. Now, after understanding what is the lines of force, let us learn about the properties or characteristics of lines of force. So what are the properties of lines of force means? These lines of force always originate from the positive terminal and terminate at negative terminal. That means from positive they start and they end at negative. So by this we can understand this curve is a discontinuous curve. You might have heard about the lines of force when you're reading about the magnetism. There in the magnet, the line of force will start from the North Pole and they reach the South Pole, and inside the magnet they move from north to south. Here the curve is the continuous. But in our electrostatic forces, here the line of force is starting from the positive terminal and end at the negative terminal. So we'll be calling this line of force here in this electrostatic force as the discontinuous curve. Okay, and then the next is, already we talked about this. We are just defining this line of force. We said that the tangent drawn at a point to the line of force gives the direction of intensity of electric field. So that will be our second property. The tangent at a point on the curve gives the direction of electric field intensity at that point. Don't simply say that at direction of E and just don't stop it there like that. At that particular point, already I said you at each and every point, usually if it is a curve, the direction will change. If it is a curve, the direction certainly will change. So tangent at a point on the curve is the direction of electric field at that point. So if this is the curve and if you want to find the direction here at this point P, if you want to find the direction at point P, draw a tangent there. Draw a tangent, and this is the direction of electric field intensity at this point. Okay. Now coming to the third one. If you see the lines of force, these lines of force will never intersect. If they intersect, we can understand this by just going in a controversial manner here. The line of force, if they intersect, what happens? So here, let us see here, it's a line of force, and we are going with the other line of force, they are intersecting. And here, at the point of intersection, the point P is there. You just consider this curve, this curve. Here we are drawing the tangent. And basing on the tangent, the electric field intensity will be in this direction, in that direction. And for this curve, to draw a tangent, the electric field intensity is in this direction. Just see there, at a particular point, the electric field intensity is having two directions. How the electric field intensity at a point can have two directions, it's quite impossible. So that's why, because electric field intensity at a point can't have two directions, we have certainly have only one direction, so this should not happen. This should not happen. The lines should never intersect. So lines of force never intersect. So this is the property here. And by looking at these lines of force, we can tell about the intensity of electric field. If in a region or in a particular area, if the lines of force are closely packed, that means, suppose if you just take any conductor here, and if you see the lines of force are like this. So it is like this was some region A, B, C, D. So see here, the region A and region C, their lines of force are closely packed, densely packed. So here we can say the field intensity is more. So it is densely packed. Field intensity is maximum. And in the case of this B and D here, regions, look at the region here. Here the lines of force are less, that means weak. So that's why you can say that if they are weak, they will be minimum. That means the electric field intensity is also weak. So by looking at these number of lines of force, they are closely packed, and we can say there the electric field is intense, immense. That means strong, more. If the lines of force are less dense, that means very few lines of force are there, we can say there the electric field intensity is weak. And if you see these lines of force, how they originate from a surface and how they terminate from a surface. Let us take this as the property 5. Always they originate or terminate from a surface at right angles. So here, suppose if it is the positive terminal and if this is negative terminal, always they leave at right angles. That means they originate at right angle and they reach here at right angle. Whatever may be the surface, at that particular surface at that particular point, the line of force certainly will make a right angle with the surface. So this is one point. And next, an important point here. This you can understand by diagram. Suppose if a positive charge is there, and if I am keeping conductor a conductor, so this is a conductor. So if you see the line of force coming from the positive charge here, it will reach here. You see here, the line of force are not entering inside this conductor. The lines of force does not move into the conductor here. So the line of force will not pass through a conductor. Will not pass through a conductor. And here, a very good question for you. If they do not pass through a conductor, what will be the electric field intensity in the conductor? 0. So in a conductor, E will be 0. So inside a conductor, the E is 0. And how to represent the lines of force for an isolated positive charge and isolated negative charge? Already we understood from positive charge, the lines of force originate. So, and they originate at right angles. So we will represent the for positive charge like this, for isolated positive charge. And for isolated negative charge, they terminate and they reach like this at right angles. So this is for isolated negative charge. Okay, and we take from positive to negative. From positive to negative. So two charges are there here. So if you want to make or show the lines of force here, so here they move first in this, and say here. And the next one here, they cannot come close to this. Always they are pushed apart, and that means they are extended sideways. They are extended sideways. So by this we can understand these lines of force are repelling each other. So they extend sideways and they contract lengthwise. They expand sideways and contract lengthwise. And this is one property what you can say. And suppose if you just take an extended charged plates, how we can see the lines of force there? Extended charged plates. That means now we have taken only the point charges and we have shown like that. And if you just take extended charged plates, let this be the charged plates here. And one is the positive charged plate, other one is the negative charged plate. So, in between these two plates, the lines of force are equally spaced and straight lines, parallel lines, equally spaced parallel lines. And by this you can understand here, the field is uniform. The field is uniform, and at the edges, they are not the straight lines, but there are slight curves will be there near the edges. So like this we can show for extended charged plates. Okay, so these are the properties of lines of force. And so let us end the session here. Okay, and in your WhatsApp group, I will post a question related to this, and then there you can do that. And let's meet in the next session. Until then, bye bye.